We're very happy to welcome Vincent Reverdy from CNRS today to talk to us about unit systems.
So thanks for the invitation. I'm very glad I can speak here today. So I will talk about unit system, physical quantities, and programming language, and not a lot about applied category theory because this is your part. I am actually looking for collaborators, and the talk should have been, the real title of this talk should have been a call for help to the applied categories committee on the topic of units for programming language. Because there is a lot of problems with units in programming language, and I will try to go through them in order to present to you like what we have been doing and why we think that applied category theory may be a good approach to solve the problem we have. And I will start with an introductory tale. So once upon a time, in a galaxy far, far away, that has nothing to do with the Milky Way, a small piece of rock that has nothing to do with Earth, a team of astrophysicists was wondering about the nature of life, the universe, and everything. And they were wondering, why do galaxies form a cosmic web? And to understand that, they wanted to run simulations to better understand what they were, how this was forming. So they did some work, and after their work, they obtained simulation like this, which was super nice. But the code looked like this. So the initialization was the only data they needed for their simulation was the simulation size, the particle mass, and some Hubble constant that will tell them how fast the universe is expanding. And then they would run their thing. The problem is that in reality, things are not that simple. And currently, in a lot of programming language, it's complicated to have units like this. And this is a huge problem because units would be, you would think, would be one of the simplest things that could be tracked by type systems. So if we look to real codes this time, this is a code that is actually in C++ that is actually used to fly airplanes. And there is a lot of problem in that code. So I don't know if you can see what the problems are, but so one first problem is that all of things are doubles. So you have no way of telling what you are manipulating. Second problem is that this function, for example, you start with the longitude and then the latitude, and in this function you start with the latitude and then the longitude. That's another problem. And another problem is that you have way too many parameters in this function, and it's very, when you will call this function, it's very hard to tell what you are doing. And this is for this kind of reasons that in real life we had failures. For example, this is a well-known failure of this plane crashing. So this was not due to software, but this was due to unit conversion between people who forgot to convert jet fuel density. So this can actually have consequence. And the most well-known example is the Mars Climate Orbiter that was destroyed in the atmosphere because the software forgot to convert between two type systems, two unit systems. And the question is, why in 2023 we cannot have units in programming language? It cannot be that complicated. And oops. And of course it can. So I'm coming here from a standardization perspective. And to describe the context, on one side, there is the standards of units that are standardized by the Bureau International des Poids et des Mesures, and the ISO 80000 that are standardizing what units are. And on the other side, there is an ISO committee for the C++ programming language that is standardizing stuff to make the language evolve. And I am actually involved in that programming language. And we are currently trying to have units, to standardize units for that programming language. And this whole project started on how to make quantities and units available in the C++ programming language. And it turned out to be a complete nightmare. So it's not the first time that people are trying to standardize units library. There are many units libraries that exist in nature. And there has been reviews on why people are not using them, and these are some of the reasons why people are not using them. So there are problems of performance, of loss of precision, of difficulty to use, of integration, of lack of concern, etc. So even if they exist, they are not used. So this is from the software side, and from the formal mathematical side, some people have been trying for years to formalize what a unit and a quantity are. So there has been several approaches. One of them is described here. I won't go into details, but this approach described in this paper tend to want to describe a unit of measurements based on positive spaces. So it's a topic of interest for several communities. In the context of the C++ standard, it's a big deal because if we manage to standardize something like this, that would be reaching millions of developers worldwide if it gets standardized. And it would be also a demonstrator for the programming language. In the context of the SI standard, if we manage to formalize something, we would have something that, let's say if we were using type theory, for example, to formalize things, then we would have something far more robust than what the SI standard is currently doing. And in the context of applied category theory, I think it is a perfect playground for ACT since it has a lot of corner cases. There is a need for a specification that can be translated into software. There is a problem of minimization of technical debt. There is a need for conceptual clarity. And above all, there is a focus on having no feature bloat. So currently, the investigation has been done in a top-down approach. So in this top-down approach, people have been investigating designs, then writing implementation from this software design, and then checking if this implementation was compatible with a lot of different edge cases. And most of the time, people find that there is one edge case that doesn't work. And what they do is that they come back to the design and they do that again and again and again. So the problem of the current top-down approach is that this doesn't seem to converge. Like we don't seem to reach a design that works in all of edge cases. So in the bottom-up approach that I would like to investigate, we would start from the older edge cases, then define abstraction based on that and formalize that. And then from the formalization, we would write a specification that would be translated into an implementation. And then we would have handled all the edge cases. And my proposal is that this applied category theory may be a good tool to do these kind of things. So, if you want, yeah.
Will you give an example of an edge case?
I will go through a lot of different edge cases. Because all of the problem is defined through edge cases. So let's start from definition of what a unit and a quantity is. So the first thing is that we have properties. And there are two kinds of properties that are described in the ISO standard. The first one is a quantity, which is a property of a phenomenon, body, or substance, where the property has a magnitude that can be expressed by means of a number and a reference. And there are also the nominal properties, where there is no number to describe them. And there are two main types of quantities. The first type are ordinal quantities, like the earthquake strength on a Richter scale, where there is only a total ordering relation, but no other algebraic operation on them. And most of the quantities are non-ordinals, which means that they have, on top of their total ordering relation, an algebraic operation, like length, mass, radius. Okay? So these boxes are the quantities that we are used to manipulate. And then quantities can refer to two different things. The first thing is the general quantity, which means the concept in terms of, for example, length, mass, radius. And then an individual quantity, which is an instance of that concept. For example, a length of a particular road, a mass of a particular block, a radius of a particular wheel. So I'm continuing to go through definition. So as I was saying, a quantity is described as the combination of a number and a reference. So the reference can be three different things. First possibility is a measurement unit. For example, meters, kilogram, meter, 1/meters, or also dimensionless quantities are also included in that framework. Second thing is a measurement procedure, and we don't usually use them. Like personally, I never use them, but this is an edge cases. So, for example, the Rockwell-C harness, which can be expressed like this. Or the third thing is a reference material. For example, the amount of substance concentration of lutropin in a given sample of plasma in that very weird unit. And the number can be, as described in the ISO standard, as a scalar, a vector, or a tensor. And when you combine all of these things, you get a quantity value. So if we restrict the thing to measurement units, then a quantity can be expressed this way. So a particular quantity is, so you describe that with a symbol. Then this is the symbol for the numerical value, and this is the symbol for the unit. And for example, if you take the mass of the sun, your symbol for the numerical value is this one, which is equal to the numerical value, and the unit is kilogram in that example. And then there are system of quantities and units. So a system of quantity is a set of quantity together with a set of non-contradictory equations relating those quantities. So to build these systems, we need base quantity. So a base quantity is a quantity that is chosen, that is in a subset of those quantities, where no quantity in the subset can be expressed in terms of the other quantity within that subset. And a derived quantity is a quantity that is defined in terms of these base quantities. And an example of that is the international system of quantities. And based on that, we have system of units, where built in the same way with base units and derived units. For example, for base units in the SI system, we have meters, kilogram, seconds. And as derived units, for example, we have meters per second or meters cube, etc., etc. And these two things are the building blocks of what would be needed in programming language to be able to handle quantities. And then there is a last thing, which is the quantity dimension. So the quantity dimension corresponds to an expression of the dependence of a quantity on the base quantities of a system of quantity as a product of powers of factors corresponding to the base quantities. So in practice, we have a list. So the dimension of a quantity is a list of dimension symbols together with exponents. And for example, in the international system of quantities, the dimension of a force can be written as length, mass, time minus 2, and same kind of things for density. And the dimensionless quantity is a quantity for which all the exponents of the factor are corresponding to 0. Okay? And there are several quantities in the international system of quantity that are dimensionless, like planar angles, solid angles, refractive index, mass fraction, Mach number, etc., etc. So currently, there has been a revision of the SI system in 2019. So this was the old SI system, and this is the new one. And the main difference is that the new one has been built using fundamental constants of nature, which for whose the values have been fixed once and for all. And it's not, for example, the old system was relying on an actual physical kilogram, and the new one is not relying on that anymore. So the way it's built, the way it's built is that we start by this frequency that of the ground state hyperfan structure transition of the cesium 133 atom that is defined exactly with this constant. From that, we deduce the second. From the speed of light, we deduce the meter. From the Planck constant, we deduce the kilogram. From the Boltzmann constant mixed with those three, we get the temperature, the Kelvin. Then we can get the elementary charge using E. Then we have the luminous efficacy of monochromatic radiation that gives us the candela. And then, by itself, we have the Avogadro constant that helps define the mole. And this is currently the system of SI and how it's built from all these constants that are currently exact values. So there is no uncertainties anymore on these values. So these were the definition, and we would guess that only from this definition we could define our unit system in programming language, and everything would go well. The problem is that there are a lot of corner cases in practice, and I will go through some of them to describe what's going on. So the first thing that may be problematic is the kind of quantity. So it's defined in the ISO standard as so kind of quantity is an aspect common to mutually comparable quantities. So for example, for a quantity of kind length, we have several different types of quantity, like width, height, radius, diameter, thickness, and distance. For energy, for example, we have kinetic energy, potential energy, mechanical energy, or heat. This is fine, except that the division of quantities into several kinds is to some extent arbitrary, and that's what the standard is saying. So the first question is, can we classify these things as set, or do we need to be hierarchies? And for now, I don't know. Like some people have been investigating describing quantity kinds as sets, some other as hierarchies. Yeah.
I mean, naively, I wouldn't expect that like the distinction between like kinetic and potential energy would be incorporated into a unit system. That seems to be so. Is that something that you think should be encompassed by a standard for units?
So this is exactly what I will describe. It all depends on the context, because in some context it's not a problem, in some context it is a problem. For example, in some context, so adding length, let's say we have two lengths, we are adding them and putting them into a third one. This is fine. This is never a problem. For radius, this is not a problem. But let's say that now you want to add length, a width, and a height into something. So in some context, in most contexts, this is probably fine. But in some context, where, for example, the height has a very particular is a very particular case in the kind of system you are trying to describe, then it may not be fine to be able to do that. Yeah.
At the post office, we multiply them together.
Okay.
To get the
That works too. And for example, in other contexts, if you are trying to add a radius to a height, in some context that may not be fine. And the thing I want to highlight is that all of that depends of the context. Like correctness of operation between quantities is context dependent. And in other, I will show more problematic cases. So second thing is that the same kind generally lead to the same dimension. But if you have the same dimension for some quantities, they do not necessarily correspond to the same kind. For example, the energy and the moment of force, they have, the two of them have the same dimension, but in some contexts in most contexts you don't want to mix them. Same thing for entropy and heat capacity, and same thing for frequency and radioactive activity. So for example, if one user is trying to add 1 becquerel, which is a radioactive activity, to 5 hertz, this is probably not fine, what they are trying to do. But because all of them have the same dimension, this is probably fine to do an explicit cast to second minus 1 so that you want to add them. So this is a clear case where it's not okay to add them, but in some real scenarios, as I was showing before, sometimes you may want to add length and width, and in some others, not really. So another question is about numerical precision. So let's say you want to add 72.5 meters to 96 centimeter. The question is the quantity you will have, should it be meters or centimeters? Like, it's not, again, it will depend on the context. You can arbitrarily say that everything should default to meters, but for some users, they may want to default to the smallest unit. So if you add kilometers to millimeters, this is probably fine. But a megaparsec, so this is the distance between our galaxy and the Andromeda galaxy. So megaparsec is a huge unit. And if the user is doing this operation, multiplying 1.75 meters by 10 to the 22nd power, then it will probably overflow, because here you will have meters, and then you will lose precision. So again, it depends on context. So even the case, as I was describing here, even in the case of common units, what you are doing is non-trivial. And for numerical precision, in some contexts, you may want to maximize precision, while in some other contexts, you may want to maximize speed during computation. And the users, if you're standardizing some unit system library, there should be a way that the user may specify that. And also, should there be an implicit or explicit conversion between the floating point types that are representing the numerical value? This is another layer of the problem. As I was saying before, this is, again, context dependency, where the choice of common units depends on the context, and the choice of how to handle numerical precision depends on the context. Then we have named units. So some units have special names in the ISO standard, for example, newtons or joules. This is fine, except that let's say that one user of C++ is using this hypothetical nice library to write that. So there is a force in Newton, there is a mass in kilogram, and there is an acceleration in meters by second squared. This is fine. And then the user is printing F and M times A. The question is that how do you manage how it will be printed? Because here, since the user, since it was in Newton, it's really fine to display Newton. But here, should it be printed as newtons or as kilogram per, times meter times second minus 2? And if you want to print newtons, that depends on context, because in some contexts, this is not a force, what you're doing. So to be able to do that, there is a need for tracking units in calculation in software. So with the question of when does this unit is automatically replaced by newtons. And the big question is, how can we make this mechanism customizable? And then we have unit simplification. So in cosmology, the rate of expansion of the universe is described by the Hubble's constant, which is expressed as 73 as in kilometers per second per megaparsec, which means that a megaparsec, which is a very huge distance, every second grows by a certain amount of kilometers. Okay? The problem is that the dimension of this thing is t minus 1. This is the invariant of the length of a time because the length cancel out. So it could be, in terms of the SI system, it could be expressed in 3 different units, none of which are probably the right thing you want to have. And this is a problem of unit collapse, which is, for example, in that example of code. If the person is doing a speed divided by a distance, then it will probably display it in second minus 1, while in this case, you would like to keep this unit. So again, the question is, how do you specify that how do you make that customizable so that in some cases, you keep track of the original unit, and in some cases, you don't keep track of them? So another instance of unit collapse is, let's say you have a simulation box, you are running some physical simulation, and you are dividing all your length by the size of the box. Okay? So the natural thing to have is that then the dimension of D is 1 because you are dividing 2 lengths. But in some context, it might be important to keep track that at first it was a length divided by length, because some functions might expect some ratio of length, and in that case that would be allowed, while if you have lost all your information about your dimension, then you can probably put that in a function that is taking an angle as an input. And this is a problem. So as I was saying, non-simplified unit expression may contain more information than their simplified counterpart. And again, unit simplification is context dependent. And the question is, how do you perform unit simplification automatically in software depending on the context? And then there are unit systems and custom systems. So there are several examples of common unit systems. For example, the SI, the imperial units, United States customary units, CGS, MKS, etc., etc. So first, a remark on prefixes. So prefixes probably need to be defined outside of unit systems, because kilogram, because some base unit of some unit systems include prefixes. And also, if you are trying to build a mechanism that can build names from prefixed units, then for hectares, for example, we have a problem. And depending on the unit system, the choice of base units of similar quantity kinds may be different. For example, the kilogram in SI versus the gram in CGS, or the meter in SI versus centimeter in CGS. And you may have a very peculiar problem when, let's say, you have a user that is taking 2 libraries, one that is speaking in SI, the other is speaking in MKS. And they are using meters in both cases. What should the expression return if you are adding meters from SI to meters from MKS? It should probably return meters, but from what unit system, it's not clear. And there is one question of how do you mix 2 different systems? And also, how do you allow users to customize and to build their own unit systems? And also, should unit systems be defined as opened or closed? So in C++, that would correspond to namespaces, where the user can reopen their namespace to add more units, or classes, which would be defined once and for all. And if we go to like more questionable problems, there is the interesting case of the astronomical unit. So this is defined as roughly the distance between Sun and Earth, and historically it was defined as the average of Earth aphelion and perihelion, which is fine, except that over time of course, with new system of measurements, the value got less and less uncertainty, which is fine. So let's say that we are working with these astronomical units, which, by the way, is included in the SI. So let's say we have some data that is coming from an old experiment. And we have new data in this astronomical unit that is coming from a new experiment. Then there will be a problem if you do an operation with these two distances, because in between, as I was showing before, in between, the definition of the astronomical unit has changed. And this is also the case for SI, because, for example, before SI 2019, the number of decimals of kilograms behind the constant that is behind kilogram was different than before. And also, if we are talking about the astronomical units, there are variations on the orbit of Earth, long perturbation coming from other planets. So if the unit is defined as the average distance between Earth and the Sun, this is a problem. But thanks to the International Astronomical Union, since 2012, the astronomical unit has been defined by one exact constant. But if your software is mixing this definition of astronomical unit with other definition, then you probably have a problem. So as I was saying, this is also a problem for SI, because in SI prior to 2019, physical constant measurement gets refined over time. So if you mix kilogram and Kelvin from SI 1960, how do you mix that with kilogram and Kelvin from SI 2019? And this is the kind of measurement refinements you get. So in most cases, you probably don't have a problem, but for people who are doing high precision metrology, that might be a problem. And then you have more rapid unit conversion factors. For example, if you're trying to convert euro to dollar, then your unit conversion factor should be adjusted in real time. So this is a completely different problem now that you have. Switching to something different regarding edge cases. So there is a common practice in theoretical physics to use natural units. So for example, in high energy particle physics, a lot of people say that that a lot of constants are equal to 1. Same thing in general relativity, where you can say C equal G equal 1, and we write your equation by removing some constants. This saves time. So behind that, there is a motivation that makes equation easier to handle. It's closer to fundamental physics. It's easy to find constant back using dimensional analysis. So this shouldn't be a problem. But in reality, in some cases, it's not so straightforward to find constant back in practice. There is a loss of information for dimensional analysis, because if people were using dimensional analysis to check their equation, then if you have a mistake in your equation, your constants are probably completely wrong. And as I said, some errors cannot be traced anymore by pure dimensional analysis. So, for example, one thing that would be fine would be to play in a space where you define your length as light year, your time as year. Then your speed is 1 light year per year. And if you do that, then all your equations are probably fine. But if you say that dimension of your speed is 1, then a type system will deduce that the dimension of time is equal to the dimension of length, which will lead to the fact that dimension of energy is the same thing as dimension of momentum. And there is a law in physics that tells you that there is a given, like Noether's theorem says that there is, on a given system, there is conservation of energy and conservation of momentum, which means that if you collapse these two things, then you have a collapse of usual physical concepts, and you lost one conservation law. And this might be important, for example, to distinguish between elastic collision or inelastic collision, because in elastic collision, kinetic energy and momentum are conserved, while in inelastic collision, kinetic energy is not conserved, but momentum is conserved. So again, if a human is doing that, there is probably no problem, but if a type system is doing that, then the type system should have a way to keep track of what's going on. One way to see the problem is to that has been explained in this paper is that there are two sorts of equation. There are complete equation and unit-specific equation. So complicated equation are expressions that are independent of unit systems, and they are compatible with any coherent system of units. So all these equations from physics are complete equations. And unit-specific equations are expressions that depend on a given unit system. So, for example, when you are doing natural units on non-dimensionalization. You can see that in computer science from a completely different perspective, and you can see that as an information compression problem if you have case symbols to track what your units are, and you have a probability P of making a mistake between one line and another, then you can see dimensional analysis as an error correction mechanism. And when you are doing unit-specific equation, you lose some power of dimensional analysis. And there is a big question when users are manipulating both complete equation and unit-specific equation in two different unit systems, is how can we inform the type system how to convert a unit-specific equation to a complete equation? Is it even possible? And in a lot of cases, it's very hard to do. Going through other edge cases, for example, the cases of angles. So plane angles and solid angles are things in physics, in geometry. So in the SI, radians and steradians are defined as dimensionless. And there is an open question of should plane angles and solid angles should be treated as dimensional quantities or not. And contrary to what we could think, there is a big debate on that. So these are all the papers I could find that are discussing whether angles should be treated into SI or not. And this can be viewed as a problem of complete and unit-specific equation. Because if we introduce a new angle constant theta n, which we put equal to 1 radian, and we can rename other physical constant, then we can transform unit-specific equations which are currently the equations that are used in physics to complete equation, where theta n is used to keep track of the dimension of angles. And in that frame of reference, then energy and torque, which have the property of having the same dimension in the current SI, suddenly have two different dimensions. So this proposal that has not been adopted would allow to distinguish between, as I said, unit-specific and complete equation regarding two angles, and introduce new concept and new way to check equation in physics. And then there is a problem of temperature. So there are several scales of temperature that exist. And these scale of temperatures are defined mixing several things. So what you need is a hotness series and fixed points that are both ordered countable sets dense in themselves. Which the combination of these two things lets you to define several scales, but to choose scales that would allow to treat temperatures as regular quantities, there are two additional things that you need, which are ideal heat engine and ideal gas. And from that, you get a temperature scale that can be used as somewhat regular units. But there is a problem. Because contrary to, let's say, when you add kilometers to meters, does it has any meaning to add 78 Kelvin to 28 degrees Celsius? So this, of course, has some meaning, and this probably has some meaning also. If you have a difference of temperature, then you can probably add that to kelvins, and the reason for that is because temperature are actually two things. There are the concept of temperature points and temperature differences. So here we have a temperature difference that we can add to temperature point, and that makes sense. And temperature scales can be defined, can be represented as affine spaces, where you have two things, quantity points and quantity differences. And you have the same thing with dates, for example. And this is something that you don't find, for example, in kilos or meters or whatever. And then there is also the peculiar case of amount of substance, which depends of the substance you are measuring. So this is a unit-dependent, substance-dependent unit. So the old SI definition was saying that the mole is the amount of substance of a system that contains as many elementary elements as there are atoms in this mass of carbon-12. And now this is defined as anything that has this many Avogadro number elementary entities. But contrary to other quantities in the SI system, you need to specify what you are actually counting. So, for example, in hydrogen atoms, you are, of course, counting atoms. It can be molecules, it can be ions, it can be electrons, etc. And this is a counting quantity, which can seem weird because you are just counting things. But the definition of the second also relies on counting something, as I was described when I presented the SI system. Then we have logarithmic quantities, for example, Nepers and decibels, that behave differently from other units. So I won't go through details, but they are well defined to the SI system. Then we have ordinal units, for example, the Richter scale and the Scoville heat scale. So these are units that someone may want to use, but they behave differently than the other ones. And if you want libraries that deal with quantities, of course you may want to deal with uncertainties. And uncertainties bring a lot of new complexity. This is how do you note them, how do you compose them with units, how do you handle measurement errors, and you automatically propagate your uncertainties into your computation. And finally, the last one is like you may want compile time and runtime checking. At compile time with zero overhead, with nice error message. So, for example, a user that would define their quantity as 8.5 meter, then read some data, and check if that can be convertible to a length. So in that case, we know at compile time that this is there should be a compile time check. But in this case, since we are using data from elsewhere, the check needs to be done at runtime. So if we want runtime check, we need, of course, runtime quantities and runtime units. So this probably needs to use polymorphism. And if you want to mix both in C++, for example, it's not that easy to do both compile time and runtime. And this is all the little problems you may have in unit system that I just listed. So the question is, how can we formalize that into a mathematical framework? So there has been several attempts. So, and I won't detail them. The first one was through semi-vector spaces and positive spaces that let define a unit of measurement as a generator of a scale space, which is itself some type of positive space. Something through scalable monoids, scalable commutative monoid, where they define a quantity space as a finite dimensional free scalable monoid over K, which has a finite basis. And elements of a quantity space are quantities. Then another approach is through sober topological spaces, where they define measurement spaces with this with all these properties. And then through quantity space where they define actually a system of units based on a space of quantities. And all of that to say that there has been some approach to try to define units in terms of mathematical spaces. And this can be done also in type theory. So I found only one paper that describes lambda D, which is a simple type theory indexed by dimensions, where they create dimension context with some like formal definition of types and formal ways of defining the terms and type context based on these types. The problem with all these formalization attempts is that most of the time they are top-down approach, and there are more formalization that, to my knowledge, ignore all the edge cases or most of the edge cases I listed before. I couldn't find any straightforward connection to practical use, so for physicists it's completely unusable, and there is not even any software implementation that are based on this kind of formalization. So what's the current, as I was describing before, the current status of units library investigation is that the top-down approach that is currently investigated doesn't seem to converge to anything. So the project I am starting is that I would like to explore the bottom-up approach using applied category theory to look for mathematical structure of the quantities and units we are manipulating. And if we are looking for edge cases, we are also looking for constraints on our type system. And in C++, it can be framed in the following way. So we are trying to build a library that has at the same time genericity, performance, and expressivity. So our aim is to be at the middle of that. So an example of a performance of a language that is performant but lacks genericity or expressivity is, for example, the C programming language. When you have regular expression, you can express a lot of things in a very small number of characters, but you lack performance and genericity. And Haskell probably lies in between genericity and expressivity. But the kind of library that we are targeting would be a library that would combine all these three properties. So the design principle that should go behind such a library would be conceptual purity. So we would start from a mathematical formalization and cover as much edge cases as possible. And aim for performance, which means that at compile time there would be zero cost abstraction, and at runtime there would be polymorphic units whose performance would be as low as possible. We'd aim for expressivity, looking at what people actually want to write, because that's what matters in practice. And in genericity, try to cover as many use cases as possible with a small set of abstraction. And different users will see different things. So for the classical user, it would work out of the box, meaning that there would be nothing to specify. It would work as expected. For advanced user, there would be a lot of customization points to describe in which context they are doing operation. is it a context where it's okay to simplify some units? Is it a context where you want to maximize performance over accuracy, etc., etc.? And for compiler writers, the compiler should work as a theorem prover behind the scene to ensure that the units you are manipulating make sense and the quantities you are building make sense also. So the way we can see that is that at first there is units and quantities, conceptually, that have had an implementation in terms of international standards of units and quantities themselves that have been translated into units library into different programming language. So depending on the kind of formalization we are doing, we can either focus on trying to design a particular software library that would work in a given programming language. Or if we reach higher levels of abstraction, then we could target, for example, writing the thing in pure type theory, then we could probably target a lot of programming language at once. Or if we formalize the thing probably in category theory, then we would probably be able to redefine more clearly what is currently being defined in international standards of units and quantities, and even tackle some philosophical question about what units and quantities are. Because this is still an active debate, and some questions that are still open for philosophers are whether quantitativeness is either reducible to qualitative features or a new feature in itself, whether it's a feature of concept dependent on the ability to construct a measurement procedure or whether they exist independently of the ability to measure them, and whether its quantitativeness is a feature of possibly any attribute or it only corresponds to certain classes of attributes. So these are currently open questions in philosophy, and trying to investigate what are the underlying mathematical structure of units and quantities may allow us to put constraints on some of these open questions. And to conclude, so to summarize, unit system and quantities seem like a trivial question for software libraries, but they are insanely complex problems with a lot of edge cases. There is no existing software library that tackles the full problem actually in any of the programming languages that I've looked for. There is currently an investigation through the C++ standard with the potential of impacting millions of users, because if such a library gets standardized, then a lot of codes could be safer in practice, and that could be useful, for example, for flying planes. So as I said, a potential to enhance software safety, and probably a good playground for applied category theory, since there is a lot of edge cases, and we could build abstraction from using a bottom-up approach. And so the next step I will be working on is probably look for collaboration and looking for research proposals. And there is a Discord server on the topic that I have opened that is currently available at this address. And I think I will stop here.
Thanks very much. Any questions for speaker?
Yeah.
Proposal.
Uh-huh.
I think it seems like you want what I wrote. I think you want a multi-sorted Levier theory equipped with a wide partial order and a model. Multi-sorted Levier theory will be your units, and all the ways you can like combine like maps between them.
Okay.
A model is like this Levier. This unit takes a real number. This unit takes a non-negative real number. And the wide partial order tells you what you're allowing yourself to cast.
Okay.
So you told yourself, I'm allowed to cast A as this or this or this or this or this. And it's partial, meaning you don't have any loops.
Okay.
And then you could let I don't know whether algebraic Julia lets you define algebraic theories, multi-sorted algebraic theories. But like if so, then it has been implemented. So there is software somewhere that does this.
I would be very interested to playing with that and try to see how I can adapt. First playing with it and in Julia, and then try to see how I can map that to C++, because I mean, if it's doable in Julia, it's probably doable in C++.
What's the wideness of the partial order?
Wideness? Every object, I don't know. It doesn't mean that there's always a map. It's just that every unit, I know what I can.
You just mean there's a wide subcategory?
A wide
that's
subcategory
partial
with
order?
a partial order.
Yeah.
I just want some maps to be called automatic casting. So if
But the casting is context dependent too, right? Like sometimes your equation, when you say like add this quantity and this quantity, it's not really complete because you
don't know whether you want to land in
answers that would
centimeters
be
or
sensible,
meters.
right?
Yeah.
Yeah.
So the
And
person
so really
that does not cover the case of centimeters plus meters, which one you should do.
right.
The person will have had to enter at the top of their file or somewhere in there, like I want the error to go from centimeters to meters or something. And so all these computations, I'm thinking will land in like the
Yeah, but
Well, I
that
don't
itself
know,
may
there
not
is-
be uniform over the entire file.
it won't
right?
be uniform.
Like the casting, no.
Yeah.
It depends on the
You
context.
wanna yeah,
Yeah, it
exactly.
depends
So
on
you
the
want
context.
context control.
Because there are two problems. There is the problem of how do you define your context, and then there is the problem of how you combine different contexts.
Right. So
Yeah.
I like the idea, like, can GATs handle basically all of this? Like there is a GAT, you know, and
Yeah,
it's not that you would have like a single, you would write like a single library that solves the problem, but you could define GATs as a system for constructing notions of quantity, like, I don't know, scalable commutative monoids or something, or affine spaces, and then you would have a standard implementation that would be, you know, a library that would be useful for most users, but you would have the way, you know, tools to extend these libraries or whatever.
Yeah, I certainly think GATS would be a reasonable tool for trying to like prototype a system like this, just to sort of see what it looks like. And yeah, you can certainly represent things like multi-sorted Lebesgue theories and, you know,
Models.
thin categories and partial orders, and yeah, and you can put those things together, and so it's, yeah, and you can get symbolic expressions for those things, and yeah, so it would be, you know, it might not be what you use to do your, you know, C++ implementation or whatever, but it could be a good playground sort of as you explore the space of possible formalisms.
Because most of the formalisms you gave would fit. All ones
Yeah.
that I think I remember you could fit there.
All
like
those
the
things
coursers.
looked like GATs.
Yeah.
They were
Yeah.
various.
Those
Yeah.
formalisms all seemed kind of bad, right? Like
But I mean, a scalable monoid is a Lebesgue.
yeah, just that like you said you feel like they basically ignore everything
Yes.
interesting or hard,
Yeah.
right? Like
Yeah.
like I feel like one of the trickiest problems is this it's not Planck's constant, Hubble's constant
Yeah.
Right.
problem of like how do you model that like a speed per length might not be hertz? Like you need to be able to divide, like okay, you got like row representations or something, and then you got some kind of dual thing, let you divide, and then but you have to say like L over L is not isomorphic to 1, right?
But
You want some kind of map probably, but I feel like you probably don't want an isomorphism because you don't want them to be the same, or they'd be the same.
But
the
it's
other
not
way
like
you
this,
can
right?
control
Like
that,
it just says how much is space expend per unit of space per unit of time, or something like quantum is expended. But that's, in some ways, you could still reasonably represent that as hertz or inverse seconds, and it makes sense. It just doesn't make sense in the context of someone trying to think, oh, my galaxies are this big, and how much is my like 1 megaparsec gallery expanding in a unit I can understand kilometers over time.
Yeah, it's like it's maybe only different in the user's head, and maybe there's not really anything mapped, but we need the math to like model the inside of the user's head pretty decently.
Yeah,
Yes.
there's
Yeah.
a question of what you want to model in the math and
Right.
what is an artifact of the computational system. Like you can think that the, you know, operations like L over L is actually equal to 1 in the math, and then you say it's just like a matter of sort of like the computer algebra of the thing, what sort of, when you normalize expressions.
Right.
Or you can say, or if you think that distinction is important enough, you can try to bake it into the math and move to some higher categorical sort of structure where those things which were equalities become some sort of
separate way of unlocking that, right? Which is that this decision doesn't need to be made at the level of a library because it's not, or a standard, because it's not contextual enough and uses context, or it is too contextual to be made at that level. And so you want to create your standard or your library so you can allow a user to resolve in the moment which context they're working in, whether they want all this stuff to be modeled from the head to be modeled in the program, or whether they can let it go. And that's something like I think GitLab and so this work around how to make some code is actually will allow that.
The kind of library I'm looking for is something that would be like a meta library, a framework that would allow users to define exactly their rules, and so that everything would be handled nicely then by user. And a specification for the SI library that most users will want, but because there are a lot of these edge cases for specialists in some areas of science, the system should let you write these more complicated cases. And for now, I have the feeling that what people have been trying to do is start from SI and try to expand SI to deal with all these edge cases. But this doesn't seem to be a process that converge.
Right. It's too fast and too complicated.
I think I might not have followed like the abstract categorical discussion, but I wonder if like part of the issue here is that like real numbers and the natural numbers are these like super overloaded concepts. And you actually you don't really want to be working with real numbers. Like people think about points in space and think about like, oh, Rn. But I feel like that's not really what you want. And I think the counting example is a really good example, where it's almost like you want the number of carbon atoms and the number of like hydrogen atoms to actually like exist in different copies of the natural numbers. So instead of thinking about the real numbers, you think about some set, maybe the real numbers maybe not the best example because they're kind of unique, but you think about like an ordered field, and like, okay, sure, maybe your temperature's an ordered field, except it's actually not, right? Like, it doesn't make sense necessarily to subtract temperature. So it's like, I don't know what structure you have there, but you think about the algebraic structure you have, and now whenever you're trying to do a conversion between, like the type system kind of rejects it by default. So you're gonna have to say, oh, I'm computing between two like ordered groups. Like, how does unit on one group map to the unit on the other group? You have to explicitly say that, and maybe like in your particular setting, you want to like set some default for the file, or I don't know, but like at least at the type system level, it actually feels like fairly well defined. And I guess I'm curious, like, are you familiar with like traits in Rust or in?
The traits in Rust are corresponding to concepts in C++, so you can do that.
And I mean, I guess to what degree is this just a problem of like defining
the whole problem
your
is
algebraic structures as like minimal traits. And so now you're not dealing with temperature as a float, you're dealing with it as like a trait that doesn't even let you do subtraction by default.
the whole problem is actually that I couldn't find any formalization of what are the algebraic structure that I am manipulating to handle all these edge cases, and in a way that is compositional, in a way that you can nicely compose them. And for now, I don't even know what they are. And this is the full problem, because once we have them, then we'll find a way to encode that in C++. It's not encoding them in C++, implementing them in C++ is actually not the real problem. The real problem is that we are not sure about what the mathematical structure we are manipulating. And it's really unlikely that people will stumble on them by chance just by extending a SI library.
We better pause the recording, but I hope we can keep chatting. Let's thank our speaker again.